Welcome to Chapter 4, Normal Distributions, Z-Scores, and Confidence Intervals. The video series hosted by me, Tim Smith, on the Workbook of Quantitative Tools and Techniques in Marketing, 2nd edition. In this chapter, we're going to be taking a look at normal distributions. We need to begin by taking a look at population metrics. Two metrics in particular we need to take a look at are the arithmetic average of a population. We have the equation here. This is the sum of the individual points divided by the total number of points. This arithmetic average of the population is exactly the same as what you would have for a sample. We're going to denote that it's for the population, though, with the Greek letter mu. Pronounce it mu, spelled M-U, the Greek letter mu. We denote population metrics with Greek letters in general. So here we have the population arithmetic average, mu, being the sum of the individual points divided by the total number of points. The equation is exactly the same we would have for a sample, except for the symbol for a sample would be x bar. For a population, we use mu. Next, we have the population standard deviation. And again, we're looking at the population. Let's take a look at our equation here. We have the square root of the sum of the variations of the points less the arithmetic average, mu, squared, divided by n. Now, the difference here is I'm only dividing by n in comparison to the sample standard deviation. In the sample standard deviation, we divide by n minus 1. In the population standard deviation, we just divide by n. So here's the population standard deviation. We're going to denote the population standard deviation with the Greek letter sigma. If you recall, for a sample, we use the letter S. For the population, we'll use the letter sigma, the Greek letter sigma, to denote the population standard deviation. Okay. Finally, we get to the normal distribution. If you recall, when we were doing samples back in Chapter 2, we saw different ways of which the metrics would be distributed. We showed those using column charts back in Chapter 2. Well, the normal distribution is how we would expect to find the probability of finding a particular measure if the measures were normally distributed about some mean. So here's the measure, x. We have the normal distribution given by 1 over the square root of 2 pi sigma squared times e raised to the power of negative x minus mu squared, so the position less the arithmetic average squared, over 2 sigma squared, over 2 times the standard deviation of the population. So here is our normal distribution equation. Let's take a look at that in Excel. Okay, so here we have a population mean and a population standard deviation. Population mean is 50, standard deviation is 5. Let's take a look at what we would expect to find the probability of different measurements. Let's start our measurements going from 0 all the way up to 100. So I'm just going to add 1 to the one above it. Go all the way down to 100 measurements. This should do the trick. Not quite. A few more. There we have it. So there you have 100 different measurements. Measure at 0, what's the probability of finding that measurement? Measurement at 5, what's the probability of finding that measurement? Remember, our mean for our distribution is at 50. Our standard deviation is at 5. Going back for just a second, we have our normal distribution being given here. 1 over the square root of 2 pi sigma squared, e to the negative x minus mu squared over 2 sigma squared. We're going to use this entire equation in Excel. So we're going to start out with equals, open parenthesis, 1 divided by the square root of 2 times pi, actually gets you the number pi, times, got to put the little parentheses there, sigma, there's my standard deviation, squared, close parenthesis, times e raised to the power requires the Excel function exp, see, exponent, returns e raised to the power of some given number, of negative, open parenthesis, I need my position less my standard deviation, close parenthesis, need to square that, divided by 2, now I need my standard deviation, 2 times my standard deviation hat, so I need to square that too. Close parenthesis, let it go. So there's my answer. What is that? Well, it's 4.1. You see that e plus 20? That means times 10 to the 20th. Shouldn't be that big. Something is wrong. It should be e to the negative 20th, if anything. exp 1 over the square root of 2 pi sigma squared. Sigma squared times e to the negative. Yeah, that sounds okay. Try another parenthesis here. Here. There we have it. Just needed one more set of parentheses. Somehow, I think it was dividing the 2 by the other portion. That's why I put in the other part of the parentheses. So this means it's 1.5 times 10, the e negative 23 here, the capital E negative 23 means times 10 to the negative 23. Well, 10 to the negative 23 is effectively 0. Watch as I put it into comma format. I get 0. Basically, my probability of finding a measurement at 0 when I have a mean at 50 and a standard deviation of 5 is roughly 0. Let's try some other numbers. I'm just going to copy and paste this all the way down. Notice I got garbage. Well, that's because I didn't put in my dollar signs as I go from row to row. Need to hold my standard deviation constant from row to row. Need to hold my arithmetic average constant from row to row. There we go. Copy, paste, and we have a bunch of zeros. Does it ever get non-zero? Yes, it does. At 39, it starts to grow. Keep going. And at 53, it seems to grow. At 50, it's very high at 0.8. These are very small probabilities. Why? Well, this is the probability of a continuous distribution. It's saying the probability of finding exactly 50 given this mean of 50 and standard deviation of 5 is 0.08. There's a chance that it has that 50.01, and that would probably also be pretty close to 0.08. So this isn't the range of 50 to 51 or the range of 49.5 to 50.5. It's exactly at 50. So you're going to find pretty small probabilities. I mean, the likelihood of getting exactly 50 on a measurement is pretty small. And after this, it starts to go down. See, now we're back at 0, and at 100, we're back at 0. We can plot this, and I'm going to go ahead and plot this. Insert a line plot. There we have it. I'm going to select my data, add the series. The series name will be probability. The series values will be all of these. Okay. And the x-axis, well, it'll be all of those. Okay. Okay. And now let's take a look at our plot. I'm going to hold this first row constant to make my life easier as I continue to do this particular exercise. To do this, I go to View, see it up here, View, and I'm going to hit Freeze Panes. And I'm going to freeze panes for the first one. Keep the top row constant. That'll work. Is that right? No, actually I want to freeze panes here. View, Freeze Panes, freeze the top row and the area. Now basically as I move around, you'll see it always keeps those first two rows because I froze panes while my cursor was here. And if I move to the right, you'll still see the first column because I put the freeze panes while my cursor was there. All right, so there's my probability. I think I might change the name of this for a little bit. I'm going to put the name up here at 50 because that's where my mean is. I'm going to title this here. I'm going to make it titled similar to what I have in the book on page 72. Actually, I'm going to use the title on page 73. Normal distribution, normal probability distribution, different means sigma equals 5. Now to get that sigma to say sigma, I just typed in S, but when I go to home, I'm going to change this font type to symbol, SYM, and there we have a nice little sigma. So there it is, the normal distribution at a, the normal probability distribution at the standard deviation, at the mean of 50, giving a standard deviation of 5. Now look at this equation. That's a lot of parts. Is there an easier way to do this? Thankfully, yes.